Hey darts fans, that's Timo Newman here, the transporter. Welcome to another video on the Good Ship Undarted Waters. We're starting a new series. That's why there's been a bit of a gap of a few days, because I've been trying to get my mind around this new series and I still haven't quite, but I've got to start. So here we go today. What's it all about? Well, this is to do with tips and techniques on how to play darts better. I've had a lot of folks in the comments section saying, can you give us some tips? Can you show us how you throw the darts and whatnot? And I will do that. But before I do that, I've got to let you into my headspace as a physicist and a sort of biology person, biophysicist, because the way that I learned darts over the last 20 months was totally informed by science. And that's kind of the point of this channel. So it's not really beneficial for you to hear me talk about how I hold the dart or how I stand, because there are professional dart players or ex-pros who can be brilliant coaches who can do all of that. I think what I can offer primarily is how do we actually improve at darts, and why is it so difficult? And that's really kind of the two things I want to get across in this series. Is how do we think about this, where first of all we can appreciate that this is really hard. And actually, in preparing this series, I've been absolutely stunned at realizing how hard this is. But at the same time, once you know the difficulties and you've got a way to represent that, that gives you a strategy then to improve. And so I hope that what comes out of this series is that folks have more confidence, that they know they're in a really difficult challenge, but they actually have some tools to improve. And by the way, I've been wanting to do a 171 for the channel to start the show, and there was a nice 171. I've just got this thing about the 19s. It comes from when I was a little kid, because I played darts for a year when I was maybe 10 or 11 against my brother, who was much better than me. But I was quite short, so I was told by my brother and dad, just go for the 19s because you're not tall enough to go for the 20s. So I always did. I didn't do very well, but it's nostalgic for me to go for the 19s. So we're probably looking at a series of 4 or 5 videos, and I'm going to try and keep them of a medium length, so not going beyond hopefully 15 to 20 minutes, because I know that when they go beyond 20 minutes it just puts some people off and they won't click even on the video because it's just like it's too much time. So in this first video I want to frame what we're talking about. I want to try and provide us with a first glimpse of the map. Because when you say in everyday language, how do you get better at something? If we think more scientifically about that, the word that comes to mind is how do you optimize something? Okay, optimization. And we all do this in everyday life. Like when you go to the grocery store, you are optimizing something. Now you might be optimizing your wallet, that you want to spend as little money as possible but get the groceries that you wish. You might want to optimize the time that you spend in the grocery store. You might want to say, well, I need these 20 items, but I want to be in the store for as little time as possible. Each of those things that you're trying to optimize, in reality, you may be trying to do both at the same time, which is really complicated, okay? But even if you're trying to optimize the time you spend in the store, that's a really hard problem. It's similar to what's a famous problem in computer science called the traveling salesman problem, which has been proven to be so-called NP hard, meaning it can't be solved in what's called polynomial time. These are exponentially hard problems. But we do these all the time in our everyday life. You go to the grocery store, you've got 20 items on your list or in your head. You may know the store fairly well. What order do you go around the store to minimize the time that you're there? Okay. So optimization is something we are familiar with, but in science, it's much more fundamental. Okay, so in this series, what we're going to do, just to give you a bit of a roadmap here, we're going to set the scene today. In the next video, hopefully tomorrow, I'm going to talk about what are called landscapes. And landscapes is the way that we can picture all this. That's going to be our kind of representation. And then in the third video, I'm going to tell you, well, how does a physicist think about all of this? And how does the physical world know about all of this? And it really does. And then in the fourth video, I will say, well, how do biologists think about this? And how does the biological world know about this? Ecosystems and organisms, how do they think about optimization? Well, how do they naturally perform in their very challenging environments using optimization? And they really, really do. So optimization is I think the best way for us to frame this set of videos about how do I get better at darts. Okay. Because my underlying philosophy is, this is not a Lego kit. This is not where you say, well, I've just got to hold the dart right. I've got to have my arm in the right place. I've got to stand the right way. I've got to have this kind of dart with this kind of flight, these lighting conditions, and then I'll play better. I think personally, my philosophy is that's the worst way, actually, the worst way to approach this. The opposite of that kind of Lego kit reductionist way is what we call holistic or synthetic or emergent, where you look at the system as a whole, okay, and realize that everything is contingent on everything else. And so it's not really about details, it's really about a mindset, a philosophy of improvement. But I don't want that to be a new age type thing, which is just words. I want to back all of this up with scientific fact, right? So I'm breathing air in this room. You are breathing air, hopefully. hopefully all the viewers are breathing air in their spaces wherever they are. That air is at a certain temperature, okay? And you may never have thought about this, but why is the air a certain temperature? Why isn't it cold in one place and warm 1 foot over? You know, why is the air quite quiet around you, you know, still in a room? That all comes from a field in physics called thermodynamics. And a principle in thermodynamics is that what we call the free energy of a system is minimized if the system is in equilibrium. So if the gas in this room is relatively in equilibrium, it has optimized its free energy. It has balanced its internal energy with the entropy and found this perfect compromise. Okay, and that's gives rise to what's called temperature. Okay, temperature comes from that optimization. Okay, and if you think in biological terms about optimization, well, goodness me, organisms, you know, you've heard the phrase survival of the fittest. Organisms have to adapt to have any chance of survival, and really survival for an organism ultimately means leaving progeny. Okay, and biologists have the term fitness for that. Okay, fitness is basically how many reproducing progeny do you leave behind, and that the more that is, the higher your fitness in evolutionary terms. So the natural world and the physical world around us are absolutely saturated with optimization. Basically, nature will always optimize. Okay, like if I take this pen and drop it, guess what? It fell and hit the floor. Why did it hit the floor? Because it optimized its energy. It doesn't like having high gravitational potential energy. If you drop something, it will fall because it wants to lower that. It wants to optimize, in that case, minimize its gravitational potential energy. And if the floor were not below it, it would fall to the center of the earth, because at the very center of the earth, it would completely minimize its gravitational potential energy. So, you know, I'm not doing a very good job, am I, at moving on with this video, but this is also cool, you know, the fact that everything on the earth would like to be at the center of the earth in terms of its gravitational potential energy. So when you optimize things, you have constraints. Okay, so the actual fact that the earth is made of something solid is a constraint. So we can only optimize our gravitational potential energy as far as the ground we're on. We can't go any further without a spade. Okay, so that's trying to frame all of this. And so for the rest of today's video, I want to set the scene. And it's going to be really fun actually doing this. And I just did it this morning, kind of written it all down. And I was kind of stunned at this. So just come on this little 5-minute journey with me. We're going to set the scene. Imagine that you've got a family friend or a family member or someone, a pal, who's never played darts, and you give them a dart and you want to try and give them a little bit of instruction about how to even kind of throw the dart. Okay, let's just go on that journey a little bit here. Let me get the whiteboard. Okay, and just check that that's visible and everything. So what I want to do here then quickly is just list the kind of things that we have to either think about or know about unconsciously to throw a dart even reasonably well. And that's then going to be the stuff that we try to use for optimization. So what is the stuff that is going to be fed into our optimization machine? Okay, so let's just call this the stuff of a throw. Okay. So the material, the atoms, if you like, the atoms of a throw. Let's break it down into 4 categories first of all. Let's think about the stance, so how you stand, the action, so basically how you move your arm, your grip, okay, and then finally I want to talk also about the head and the eye. All right. Now obviously there's no unique way of doing this, and folks who've played darts longer than I have and I really have it in their blood will have probably a better way of thinking about this, but this is just a reasonable way. Okay, so I'm not claiming that anything I'm saying is the only way it can be said or the only way it can be framed, but I'm just trying to do it in a reasonable way that we can all basically agree, yeah, that's a reasonable way to go ahead. Okay, so starting with the stance then, I'm just going to kind of scribble here. I'm going to write in my kind of handwriting here just because it's quicker. So you've got the orientation, so basically what angle do you place your feet? All right, so either head on or completely sideways. You've got the feet themselves, about how far apart are they, you know, do you put more weight on one than the other, and so on and so forth. You've got your back. Do you have a straight back or do you bend forward, and so on, okay? In the action, you can think about your elbow height, which is a really crucial variable, by the way. You've got your wrist. So how flexible is your wrist and how much do you flick it? You've got the speed of release of the dart and also the angle of your arm when you release. So basically when you release the dart, what's the angle and what's the speed? And I've got to make whole videos on those 2 variables about trajectories. It's amazing stuff. I can't wait to do that. Okay, there's so much that we can talk about on this channel. And then you've got your shoulder. Do you involve the shoulder or not? Some players do, some players don't. Then for the grip, I mean, this is a whole subject in itself, but you can first of all think, well, how many fingers are involved in my grip? And where are they placed? So the placement of the fingers. And then with the head and the eye, really this is to do with the plane of throw. I'm just going to write here relative to your dominant eye. Okay. So is that plane of throw in between your dominant eye and the target, or is it slightly off to one side or further off to one side? Okay, and those are all viable options. And then I'm just going to write head angle as well. So do you consciously try to have a head where your eyes are relatively the same height, or do you like to tilt your head and so on? All of these are possible. Now there's many more things that one could write here, okay? So this is just already some, okay? How many things do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's an interesting number. So there's 11 kind of what you might call variables there. There's 11 kind of kinds of atoms that we can play with here, or 11, you might call them degrees of freedom. If you're kind of in science or engineering, you'll know that phrase, degrees of freedom. That's a lot, okay? The best theory that physicists have for unifying gravity and quantum theory, so-called grand unified theories, the best theory they have is called string theory or M theory, and Ed Witten in Princeton is one of the big architects of that. Guess how many dimensions of space-time M theory is written in? It's 11. So you could argue string theory and darts, pretty much the same thing, okay? They need to get more dart players involved in string theory, I reckon, and probably more string theorists in darts would be very cool. Okay, so just to end this introduction then, let's just start to get a sense then of this. First of all, as we're going to see tomorrow, 11 dimensions is an enormous space. So when we talk about landscape for optimization tomorrow, 11 dimensions is unbelievably big space. All right, and we can already take from the number 11 that this is essentially an impossible problem to rigorously solve for a given individual. So already I think I can say, don't worry about perfecting your throw. You cannot. There is no, it's not possible, because 11 dimensions is way too big. If it were 2 or 3 dimensions, maybe you could do it. 11, not possible. Even with string theory, that 11-dimensional theory, they've shown that there are an infinite number of essentially solutions, and yet only one of them is the one that nature chooses. It's really incredible stuff. 11 dimensions is an unfathomably big space. We live in 3 dimensions. We have 1 time dimension. That's why you often hear about 4-dimensional space-time. 11, mind-bending, okay? But let's just finish this by thinking about, can we get an estimate, a rough estimate, crude estimate of how many different throws there are based on this? And this is really crude now. So let's just say, well, there's roughly 3 different orientations of the feet, you know, kind of like straight on at an angle, perpendicular to the line between you and the board. Maybe there's 3 different ways that you can separate your feet, you know, really close, really far, in between. You might have a straight back, a slightly bent back, a more bent back, maybe 3 different ways. So 3 times 3 times 3 is 27. So it's 27 kind of different stances already. And then your elbow height, just crudely speaking, lowish, in the middle, highish, so 3 different ways. Your wrist, fairly steady, very flexible in between. Now the speed of release and the angle is a very, very, that's not like a thing you can chunk, that's more of a continuous thing. So there's many possible combinations of that. So that's a big number actually, but let's just say for the sake of argument, there's roughly 5 different ways you can combine your speed of release and your angle of release. And then shoulder, let's just say 2, you either involve it or you keep it very still, okay? Number of fingers, you need to have at least 2 in order to grip the dart. So it's sort of 4, in a way 4, although you can use different combinations of fingers. So there's more than 4 really in terms of which fingers you use. And then the placement, how close together, whereabouts on the dart. Again, there's many ways. I'm just going to say 4 just for simplicity here. 3 times 3 is 9, times 2 is 18, times 5, that's Shanghai on the 18 segment, that's 90. And then the grip is 16. And then the head, the plane of throw, let's just say roughly there's 3. There's either directly in between your dominant eye and the target, slightly off to one side, or actually fairly lateral, okay? Again, these are crude, right? There's really more divisions than what I'm writing here. I want to give you a sense of how unbelievably big this space is, okay? And then the head angle, straight, slightly crooked, more crooked, maybe 3. See, 3 is a common number. It's just like a little bit more, or a lot. You know, none, some, a lot. But there's lots of divisions in between. So what we've got here then is 27 different stances, 90 actions, 16 grips, and 9 sort of positions of the head, eye, and the plane of throw. So we can just multiply all those together to get, well, how many throws are there? So I've done this. I'm not using my calculator with the bad battery because I don't want to waste your time. I've got it written in front of me, pre-calculated. If you multiply those, so this times this equals, and the number is this. So what I would say is, with the crudest possible kind of atomization of a throw, and with these numbers 3 meaning, you know, small, medium and large, which is really crude. But even if you do that, there are 349,920 different throws. Okay? Which one do you want? Okay? I can tell you this is why it's impossible. No one's going to find their best throw within this 1/3 of a million of different throws that they can do. You just can't. You can't even sample that in a lifetime. So when we are starting out and practicing and whatnot, we're not sampling 1/3 of a million different. And there's actually, really, you can multiply that by 100 because of all these crude divisions. So there's really many, many million different throws, like qualitatively, identifiably different throws. So there is not a best throw. So let's just park that. We're not going to worry about having a best throw. An organism does not worry about having a perfect, behavior or a perfect life cycle. We don't worry about having a perfect trip to the grocery store. The air in this room does not worry, if it was conscious, about having a perfect equilibrium. What we want to do, though, is have a good solution. Right? You want to have a good trip to the grocery store. An organism needs to be pretty fit to survive. The air in the room needs to be pretty much in equilibrium. Otherwise, I'll be pushed around by air currents and get burns on my arms from sudden fluctuations. That's not good. So nature knows that perfection is very hard to attain, but it's kind of irrelevant. What you want are very good solutions. And so this is now the framing of this whole thing. In this 11-dimensional space, which has a minimum of 300,000 points in it, but really more likely many, many, many millions. How do we find good solutions? We need a philosophy, a strategy to attain that. And that's the subject then of the next few videos informed by physics and biology examples. Right, so with that, my friends, I hope this has been helpful. I'm very excited about all this because this is my life for the last 30 years in physics and biology. It's thinking about these things, and it's wonderful in preparing this series that I've realized that my whole darts adventure has been informed by that unconsciously. I never really realized, but it has, and that's what I want to communicate with you. So 3 darts at the oche, make them count. I hope you're all doing well, and I'll see you next time.